Okay, so last time we were looking at this boat. This boat, it travels along this curve, and at different points, the position from here, the lighthouse, uh, to the boat is in a different position. It's represented by a different vector. We're looking at what we call a trajectory as this logbook. The logbook is going to keep track of all of the positions of the ship as a function of time. So it's going to know where something is here at this time, here at that time. It's a little bit different from a path. Remember, a path is just without the time information. So I could, for example, have these two trajectories, y and z, or these two paths. So if these are paths, these two paths intersect, but we don't know if I've thrown something off this way and I've thrown something up this way, whether or not they collide. Okay, do they hit each other? I don't know that. That would be very important for something like a missile defense system, right? You really want your missile defense, let's say this is your missile defense, to be able to hit this thing. So you need to know whether they collide. You can't do that with just the path. You have to have a common time coordinate for the two paths, R and S. So we have this time coordinate in there. And now what do we want to do? We want to add kinematics to our understanding of this. And when we add kinematics, what we're going to look at how these things change in time, right? So right now we just have a function that's a lookup, and we did some lookup stuff last time, and we showed how we can find things with the lookup, and you did a little problem that should help you to understand what's going on with the trajectory. So right now the trajectory is just helping us look things up. Not that important to deal. However, if we add kinematics, if we add velocity and acceleration to this, we can do a couple of things. One, obviously, we can figure out these things like the tangents to the curve, which way is the thing going with respect to the curve. It's tangent, so parallel at that point. Right? The tangent to a curve is the parallel direction, the direction the boat is going at the point ST1, right? At the point ST1, at that time, T1, the velocity is this line. It's tangent to this curve. At the time T2, when you're at this point, now you have a different tangent going in a different direction, almost opposite. And then we'll also want to find the acceleration. And that's going to allow us to connect mathematics to physics, because what we're going to do later is the inverse problem, right? Rather than taking our position and finding a velocity or an acceleration, we're going to integrate the acceleration to find the position. And this acceleration is going to come to us through the dynamical laws, through Newton's laws, basically, in this class. So we're going to be able to use this position, or this acceleration function, to build up to the position function after finding the velocity function. That's what we'll do later. But now we just want to play with the derivatives. So this is a similar problem to the one that I did a little bit earlier in the previous video. This one's symbolic instead of numeric, but other than that, it's fine. Remember, we're going to find here the velocity and acceleration. So what is the velocity? Well, I mean, the meaning of the velocity is the rate of change of position in this direction. So this is the s dot of t. that was different at different places, and they're not parallel. So this is s dot at t prime if this is s of t prime. And to find the velocity, we just take the derivative. So let's see, s dot of t is equal to ds dt. So that's d dt, and we substitute in the s, which is d over t squared. This big T is a constant, little t is the only time variable. In the y hat direction plus some magnitude times 1 minus t cubed over capital T cubed z hat. Then we FOIL, and this is just going to act the same way it did in the previous class when we just did kinematics in one direction. We do FOIL, so the derivative gets applied to each. I guess it's not foiling, that's distribute. We distribute it. It gets applied to each term. So now we have d dt, d over t squared times t squared in the y hat direction plus d dt a 1 minus t squared over capital T cubed in the z hat direction. The a gets distributed in here, so we don't have to worry too much about it. Capital T squared and d are all constants, so they come out of the derivatives. So we only have, let's see, do I have enough room? Probably not. No. Okay. So we have the derivative here basically of t squared, which is just 2t. So we have 2d over t squared, capital T squared times t in the y hat direction, plus or minus, we'll decide that in a second. Okay, we have two terms here basically, a and a over t cubed times t cubed. So we'll do both of those terms. The first one is just a all by itself. The derivative with respect to a with respect to time is 0, so this is going to be 0. This one, however, which is going to remain negative, is going to be a over t cubed. I forgot that I'm going to take the derivative of this guy, so he's going to have 3t squared in the z hat direction. That's pretty messy, so let's see if I've got a prettier solution here. So same thing right here. So remember, I took the derivative, I distributed the derivative, then I took the derivative of the individual terms. These y's and z's do not change with time, so they come out of the derivative. So technically you could have unit vectors that do change in time, but these are basis vectors for this space. They just sit there, they're always in the same direction. We don't worry about them. But if our basis vectors, if the way we were measuring was changing, then we'd have to worry about changing those things. We're not going to have to worry about that much in this class. Next we do the acceleration. Right, so now the acceleration is going to be something that is making this curve inward a little bit. Now the question is does the acceleration increase or decrease the size of this thing? So I'm not sure. I will say that this is probably the direction of the acceleration, s double dot. So let's see. So I'm saying that this positive term here, this guy, is positive, this guy's negative, so it's got to be in, the acceleration has to be in the fourth quadrant, right? If this is AX and this is AY, acceleration is in quadrant 4. So that looks like it's actually going to increase the speed. But let's take the derivative. The acceleration with respect to t is ds double dot dt, ds dot dt, excuse me, which is equal to d dt. We FOIL these things out. 2d over t squared times t in the y-hat direction. Okay, that's failing. Minus d dt 3a over t cubed times t squared in the z-hat direction. The only constant we have, the only non-constant is t here. When we take the derivative, that just goes away. So we have 2d over t squared in the y-hat direction. We have acceleration this way minus acceleration that's increasing over here. The acceleration in the z direction is increasing from 0 to something larger and larger. So 3a over t cubed dt cubed dt, the z-hat direction. So that's dt over t squared y-hat minus 3a over t cubed times 2, which would make this 6 t squared t. This is t squared. Z-hat. So, clean that up so it can be seen. We have 2d over t squared y-hat minus 6a over t cubed t is equal to z-hat. That tells us about this. It has a y component in the positive x direction, has a z component in the minus negative z direction. And that's how you do this, is you just take the derivatives of the original function to find the acceleration, find the velocity. So that's good. Again, not too difficult. You do have to distribute when you use the derivative from term to term. Anything in those parentheses, the derivative operates on. Okay, so let's see. I thought I create. Yes, I did. Here's one more for you. Why don't you try this one? Why don't you find the velocity and acceleration of the same function that I gave you earlier? I gave you 2 meters per second t I hat plus 2 meters minus 0.5 meters per second times t squared. So go ahead, take your time, put it on a piece of paper, and find the velocity and acceleration for this function here. 2 meters per second t in the I-hat direction plus 2 meters minus 1/2 a meter per second squared t squared in the j-hat direction. All right? Talk to you later. Bye now.